Is that correct, Wayne? In National
Yes, yes.
Central University in Zhongli. And yeah, it's been a while, 8 years. So hopefully when everything is stable, I can physically come back to Taiwan and visit you guys, and also in Sinica and in Chongyang. Okay, so once again, thank you, Wayne, for the introduction. Today, I would like to share to you our work on regards to looking at a very particular aspect of non-equilibrium steady states, and basically whether such steady states are reversible or not. This is kind of like a misnomer because when one says it's steady non-equilibrium, then one have something in mind, deviation from reversibility, right? But we will show that you can actually quantify that, and as a matter of fact, you can look at how far a system is from equilibrium by just looking at reversibility. Okay, so usually I begin with a discussion on where the Philippines is, but let me go straight to anyway. MSU IIT, our university is located in the southern part of the Philippines, and so if you are coming from Taiwan, you usually required to have at least 2 flights to come to our university. And we have a lot of waterfalls. So if Wayne and all of you wants to have some adventure with waterfalls, then please do visit when the when the situation allows it. Okay, everyone knows this, but I would like to share a bit of this slide. As Wayne have told me, there are some students around. So basically, in the statistical mechanics approach, our goal is to look at some properties of a macroscopic system. For example, a balloon, for example, a steam engine, or properties of some devices, things like that, by the properties of the particles constituting that system, right? And that's particularly very beautifully done in this Gibbs Boltzmann statistical mechanics approach, wherein, for example, you have the partition function here. Okay, for example, in the canonical ensemble, you have the partition function, and the partition function is just given by integrating the Hamiltonian here, where beta here is just your Boltzmann constant 1/kT, where T is temperature, right? So the beautiful part of this is that you are able to have this partition function, and looking at the physics of it, is this partition function Z actually yields the free energy. Okay, so the free energy of that system is just then given by the minus kT of this ln of this partition function. And this is very beautiful because the free energy is something you can measure, okay, in a macroscopic point of view. When you do experiments, things like that, these are the things that you can measure. But you can relate it to the properties of the particles constituting the system, right? So it's very beautiful formulation. As a matter of fact, as I have mentioned, statistical mechanics has been applied considerably well in many aspects. For example, it led to us to interpret understanding of phase transition of matter. For example, diffusion and mixing of gases or liquids, for example. It ushers the industrial evolution, that leads to the current society, highly advanced, technologically advanced society that we have, and even on discussions on those beyond this planet, like entropy of a black hole, and so on and so forth. It's very, very successful. Nonetheless, it's not the total theory that we want. As a matter of fact, much of our understanding of physical mechanics fails when we consider systems that are far from equilibrium. Okay, and I just borrowed some of these videos from YouTube. For example, these are all from YouTube. For example, you have a growing plant. So this plant gets this energy and materials from its surroundings and convert it and even reproduce. Okay, so we current physical mechanics is not able to explain this, and so we are to build one. As a matter of fact, collective dynamics is another interesting thing that we see often in nature, and which the current physical mechanics approach cannot properly cannot account for. Okay, so some of the systems, some of the questions rather, that are very essential when you go to systems that are far from equilibrium are, for example, the following. Okay, so what is temperature? For example, for the case of this collective dynamics, this is made up of this bacteria, and they create this non-equilibrium structure, large-scale non-equilibrium structure compared to their sizes. One can ask, what is temperature for such a system? Is there a second law like principle for non-equilibrium systems? There are so many other questions on regards to these systems are far from equilibrium. Currently, it's still an object of massive research. Okay. Now, one of the direct implication of systems far from equilibrium is actually this question: how far is that system from equilibrium? Because, as I have mentioned earlier, we already have a structure of physical mechanics that can explain well equilibrium conditions, and therefore our hope is that we can probably apply some of those to systems that are far from equilibrium. And so it is important, therefore, to ask how far a system is from equilibrium. Now, specifically, what this implies is that can we do a proper characterization of non-equilibrium steady states? Okay. Okay. Wei-Yin, I can just go forward, right? But if there are questions, it's kind of like an informal, right? So if
Yeah, I saw there's a hand raise.
Oh, okay.
So this is not a question. This is on the screen I can see teams.microsoft.com is sharing your screen. Stop sharing hide. So that little bar that hides something that is written beneath it, which is in your slide. So could you hide that tab?
Yes, this one. Sorry.
Yeah, sure. Thanks.
Is that okay now? Yeah. Okay.
Yeah, perfect. Thanks.
Okay. So yeah. So going back, that question of knowing how far a system from equilibrium is basically all about characterizing non-equilibrium steady state. Okay. So how do we measure a system's distance from equilibrium? Okay. So there's a very long history in regards to this, and as a matter of fact, as we are now doing experiments on various systems, a lot of this has shown some pros and cons. Okay, for example, the early development on this was Einstein himself with this fluctuation dissipation theorem. For example, if you remember quite well, you have this very beautiful relation. You have gamma d equal to kt, where gamma is gamma is the friction coefficient, d is diffusion coefficient, and then kt is temperature. Okay, so that's very beautiful. But unfortunately, in systems that are far from equilibrium, fluctuation dissipation theorem does not hold generally. Okay. Another approach that are currently being used back in the 70s is this higher order time correlation functions. Okay, although again there are limitations in regards to this, in particular on some systems. There is recently back in the development of optical tweezers by Bustamante, Retort, and the group. There are discussions on measuring it by looking at signatures of non-Gaussian fluctuations. Now, we now have lots of experiments that show that, interestingly, there are equilibrium systems that does not exhibit Gaussian fluctuations, and also that there are non-equilibrium systems that do exhibit Gaussian fluctuations. So signatures of non-Gaussian fluctuations have a very big roadblock ahead of it. Quite recently, a couple of years ago, Battle et al. Proposes to look at measurement of a system's distance from equilibrium by looking at fluxes in phase space. What I would like to share to you today is another approach, which is to look at it via the detailed balance-like relation. Okay, so I put like relation here because, again, as I mentioned earlier, instructive to note that in non-equilibrium steady states, you always have a presence of a flux, and therefore, in general, the detailed balance relation that you have in thermodynamics does not hold. Okay, but it's a detailed balance-like relation. Okay, let me proceed with this approach. Initially, this was done by Astonian and his student. And the whole concept back then was on phoretic transport. So basically, consider, for example, you have a system wherein there is a gradient of some thermodynamic variable, let's say temperature. So if you have a temperature gradient, what will happen is that the particle, you have a probe particle in it. If you can see this figure on the right side, exhibits what you call thermophoresis. Okay, so it's a motion driven by the temperature gradient, global temperature gradient. Okay, now it's quite interesting that in the case of Astomian, they proposes a form of a free energy for such a system, although a lot of discussions have already been ongoing on regards to the validity of this formulation, okay, this assumption of presence of this free energy, G, okay. But the important thing is that using the formulation that they developed, they were able to show that the probability, transition probability from one point to another. Okay, so if you choose 2 points in here, you say it's XA, the other one is XB, and you count the number of times it moves towards that, and the probability it moves towards that particular position, and reverse this one denominator. If you take the ratio of that, it gives you this exponential of this minus delta G over KT, okay, where G is their so-called free energy, okay? Now, the emphasis here is the fact that these are all time dependent, transition probabilities as time dependent, but they do cancel out in their formulation to give yields to this. Now, we call this detailed balance-like because in equilibrium, we know for a fact that this actually is governed by the detailed balance equation. So you have this one at the below. So you have this transition probability is just equal to the ratio of the steady state distributions. Okay. Of course, in the thermodynamic equilibrium systems, this is just Boltzmann distributed. Okay. This PSS is your Boltzmann distribution. Now, in this formulation of measuring how far a system is from equilibrium, the natural case, for example, is to yield this to equal to an exponential of a non-equilibrium potential. Okay, so instead of harnessing again G, it's very problematic to know whether this is a real thermodynamic potential. Nonetheless, people currently are doing that assumption of having non-equilibrium potentials on the other side here. So this is what we call a detailed balance-like relation. And this has been checked, for example, for colloidal particles under a tilted landscape. And it shows very beautiful results confirming this relation. However, not so much has been investigated, for example, for cases wherein the system is subject to active noise, okay? And this is now our contribution to this work. Now, when you say non-equilibrium steady state, it actually goes way beyond. I was very happy to have this slide because probably this is the only contribution I really have to your group, which is on quantum computing, right? So non-equilibrium steady states goes all ranges of length scale, from quantum transport less than -9, or even to galaxy dynamics. Okay, you have everywhere 10⁻³ pandemics, collective motion of birds, etc., and so on and so forth. Now, my interest in the laboratory is on regards to this time scale. It's still a very huge time scale, length scale, sorry. It's from 10 to the negative 6 to 10 to the negative 3. So we do a lot of experiments on regards to this length scale on checking those formulation on detailed bands relation I discussed earlier. In particular, our work goes to having synthetic colloidal particles. So we make Janus particles in our lab, something like 1 micron or 0.5 micron, wherein one side of it is coated with metal. And so we can actually induce some dynamics to that. And unfortunately, I don't have time to discuss this today, so I will have that some other time. This one, on the other hand, is the one in the middle. I hope you can see my cursor. Is a slime mold. So we do also biology a type of experiments and look at the dynamics of the flow. Okay, still very far from equilibrium, but and also these granular experiments. So this is now in millimeter range. Okay, so we make particles that under vibration can move in a persistent manner. Okay. So today I will talk about two types of systems that I would like to check that formulation on the detailed balance-like relation. The first one is this colloidal particle under an intermittent harmonic potential. We just submitted this work and hopefully it will be accepted soon. But we have prior work on this back in 2015 and even in 2012. And but another system that I would like to discuss is the fluctuations of a Brownian-Rachet gear. This is quite recent. We have this two results for this were published last year. Okay, and there's another one. Hopefully, we can send out soon. Okay, so let me go first to the first system, and Wayne specifically mentioned to me to discuss a bit about optical tweezers and. So I would like to showcase some very minor physics in regards to this. But in our lab, I would like to show that there are many ways, as a matter of fact, to measure force or to induce tension to systems. Okay, so in our lab, we do very basic tracer particles. This is called traction microscopy, wherein you can put some beads and you allow the system to non-equilibrium system to induce some force, and you look at how the bead responds with that. So, okay, one can do beads, another one can do pillars. Okay, so we can also make this micro pillars in our lab. You can make even now simply you can even do this with 3D printers. Okay, and you can look at how those pillars bends because of the force induced by the system. Okay. But in this today, I will be talking of our measurements using optical tweezers. Okay, so basically, this is a typical setup of an optical tweezer we have in a lab. So this one is a single beam optical tweezer, and the idea in an optical tweezer is that if you tightly focus a beam on some area, okay, some region in space, you can think of this graphic over here. So if you have put it tightly focused, so the beam profile will be like this. And if you have a particle very near to that beam, I mean within the vicinity of the beam, then depending on its location with respect to the center of that beam, it will refract light differently. Okay, so so for those sides that are away from the beam, the light refracted is not so much. Okay, of course the intensity of the beam is much on the center. On the other side, on the other hand, near the center it's much more. And so of course some of this light is refracted. Okay, and because of Newton's third law, therefore there is an equal force for both of this that yields that force, a much bigger force towards the center. Okay, and because you can make your trap 3D, okay, because you tightly focus in a spot, beyond that it will also blow up. So you actually have this somewhere in the middle. Okay, a system that looks like this. So you have a high intensity at the center. So you can do trapping in 3 dimensions, okay, X, Y, Z. So that's practically how optical tweezers work. Of course, there is a much deeper theory on this, depending on the size of the particles that you would like to trap with regards to the wavelength of the trapping laser. In our lab, we not only do this type of one trapping beam. We have another setup that can do even much more intricate types of trapping using holograms. Okay, so we also do structured light illumination, in particular holographic optical tweezers. And by you know that light is not only intensity, right? It's also about phase. And so by changing the phase, you can trap many particles at the same time. So in this setup, one of our crudest setup, you can have one trap. But here you can see this is the logo of IIT, our university. You can make multiple traps at the same time. Okay. And not only that, using holographic optical tweezers by just changing the phase in the spatial light modulator, which we do in our lab here, you can actually make things move. Okay, so this is what people call optical vortices. Okay, so these are some experiments done by my students. Okay, so you can change the angular momentum and rather you can set the phase such that it behaves like a Bessel function, and you will have this type of rotation. Okay, so you can actually make this rotation static, or like in the one in the bottom, you can make it move. Okay, so you have dynamical control. So these are very interesting things, but as I mentioned, these are very small particles, about 1 micron to 2 micron to 3 micron. Okay, that's the typical sizes of these systems. Now, I'll go to the physics that, in particular, that we are trying to do. For this one, we use this another setup precisely because we would like to have a very controlled system. Okay, so we made a dual optical trap system, which is actually part 2 of this work that I will be talking. We will be doing double well potentials. But today only single well. Okay, I'll discuss single well. And the idea is that from this setup, we can actually control the distance from one to another and move them up in space. So this setup that we have a laser, and this laser goes through this splitter. You have this beam splitter over here. So you'll now have 2, and these are cross-polarized, so P wave and S wave, and then later on we can recombine all of them back towards this microscope which we made. So basically this is a system that is quite stable, so we can have stability of better than nanometer here. Okay. Not only that, in the one of the things that is very important in this setup, precisely for this results I will going to tell, is the presence of this shutter. If you can see this one over here, this is actually a mechanical shutter that cuts this light on and off in a process. Okay, so that's how we generate an intermittent potential. So as I mentioned, we use a shutter along the path of the lasers, and we can turn it on and off as in time. Okay, so the important thing is that we can control, for example, the probability distribution of the period of the on-off, and it follows a telegraphic process. Okay, so you can see in the distribution here that they follow the exponential distribution, wherein the average period of an on and off state is given by this, how do you call this range in the on state, and chi is given by from 1 to 2.7. So you can just recover tau off for that. Okay. Now, because you are now having your potential turned on and off as a function of time, Initially, your particle is centered. It's trapped in the center, but because at times there is an off state, then the particle can then diffuse away from the trap center. And we would like to analyze this and look at, for example, the corresponding non-equilibrium steady state and the reversibility of such non-equilibrium steady state. Now, this is a typical raw data. So if you have x, the position along x as a function of time, and you can see over here that depending on the values of this chi, then you can see rather huge fluctuations for chi equal to 1, wherein the periods of the on and off are the same. But this gradually becomes smaller when you have on state. Of course, the equilibrium condition happens when tau on, rather tau off is 0 or chi approaches to infinity. Okay.
Sorry.
Yes, please.
I have a simple question. So why do you need to control on and off? Are you going to make it diffuse or control it in the center? And what's the P here, the survival probability?
So probably you're referring to what they call resetting problems, right? So the idea in resetting problems is that basically you turn it you turn it on off, and then the particles reach some moment, and then you move them back. So we don't do that here. So basically the potential is just set on and off as a function of time. And the idea why we have this model is because this is typically how one can see, for example, active systems. In active systems, for example, collisions between a certain probe particle and the medium, for example, bacteria, follows a telegraphic process. So our interest is on regards to that type of process. So we do not do moving the trap center. We don't do that. We just turn on and off the laser stochastically.
Okay, and then what's the P here?
This is sorry. This P is just a probability distribution of a certain period. Okay, so if you can look at the inset, for example, it's too small, I think. The inset, for example, you can see on and off. So the amount of time it is on is just your tau on, okay? And the probability distribution of those tau on and tau off is just given by these curves. So
okay.
P tau here is the probability distribution. So that's the probability, for example, that's the probability of, for chi equal to 1, the probability of having tau on equal to 0.6 seconds is about 0.05%.
And the probability distribution is respected to certain region, right? Or do you define a region to see the probability?
This probability is actually from the data from the experiment, so you can control this. So this is the on and off of the laser. So you actually put this in a computer, and you tell the shutter, mechanical shutter, to on and off based on this probability distribution.
Okay.
Yeah.
I see.
So the response, I think you are referring to the response. The response, on the other hand, is one on the left side, which I will also discuss much deeper later. So the response of this on and off is you can see by eye on the left side. For example, if you turn on and off the laser in such a way that the period of the on is almost at the period of the off, then the particle can actually go out of the trap center more compared when the tau on is high. Okay.
I see. Thanks.
Yeah. Okay. Sorry, I cannot really see you guys. It's my first time to use this Microsoft Teams, right? So sorry, I do not know your name. Sorry, but let me proceed. Yeah.
Okay, I'm in. Okay, thanks.
Okay. So, well, going now, so as I mentioned, this is now the response of the particle because of this turning on and off the laser. And you can actually see this fluctuation. You can track this particle, okay? So we make our software to track this particle, and we have pretty good resolutions on those trackings. And from those trackings, you can actually calculate the steady state distribution. So what you see here in A is the probability distribution of a particular position of the particle as a function of chi. Okay, remember chi is about higher chi meaning higher periods of on than off, and you can see here that at equilibrium condition at chi equal to 1, this is the one in the middle, and it perfectly fits by a Boltzmann distribution, okay, as expected. So we know already in statistical mechanics, if you have a harmonic oscillator, for example, and in the thermodynamic limit, that oscillator will be just given by the Boltzmann distribution, where you have e to the negative u over kt. And so you have something like minus 1/2 kx squared over kt here, okay? So we did recover the equilibrium condition wherein there's no turning on off the laser, it's just turn on all the time. However, for those protocols that you indeed chop the laser, you see that there is two, how do you call this? Two components of the steady state distribution. Okay, so you have this Gaussian component over here, and also this non-Gaussian tail. As a matter of fact, these are exponential tails. Okay, so from these Gaussian and non-exponential tails, you can, for example, calculate the transition from this Gaussian to non-Gaussian tails, and this is what we call theta. And as you can see, if you measure theta for different experiments, trials, you will find that it perfectly fits around this region over here, okay? And as a matter of fact, you can take the average, and that average is very, very close to this 0.075 micrometer. But we know that this length scale is actually related to the optical trap length scale. From the optical trap, you can calculate the characteristic time scale, which is just kappa over gamma, where kappa is the stiffness of the trap and gamma is the friction coefficient, which is a property of the fluid. And what you get is this value also. Okay, so perfectly well. So this is quite equilibrium. The non-equilibrium component, on the other hand, is observed beyond theta. Okay, so if you go beyond theta, you now see these exponential tails. And again, you can fit this with a decay constant. For example, just to characterize this, so you have R, and you can see that as you increase chi, this R decreases, and at equilibrium condition, this goes to 0, right? So you fit perfectly well here. Now, calculating the steady state distribution given our protocol is not trivial. As a matter of fact, it's quite difficult to get analytical results on regards to this. Simulation wise, no problem. So we did some simulations, and that is what the solid curve that you can see over here. Analytical form, on the other hand, is not yet done. But what is important that we see in here is that the steady state distribution shows us these two particular components. Okay. Now we would like to check whether that steady state distribution is enough to characterize this system. And one way to check that is actually to perform other types of tests. And one of them is just by calculating what they call the mean square displacement. And the other one is the autocorrelation, okay? So, for example, if you have a harmonic oscillator, and assuming that you have an effective, a particular trapping stiffness, kappa, in a temperature T, one can calculate the mean square displacement, and you can actually get this result. Okay, so this is purely for equilibrium condition. And as you can see, this is just a function of this effective trapping time scale and stiffness. Now, what you can do is you can actually plot this out. You perform that analysis in our particle trajectories, and you will get this result over here, this C. And the beautiful thing is that if you properly normalize it, for example, with effective time scale, they will rest in one curve. Now, what does this imply? This implies that unlike the steady state distribution, the mean square displacement actually yields an equilibrium picture. Unlike the non-equilibrium, the steady state distribution, which clearly shows us the non-equilibrium details of the system. Actually, if you do the same thing for autocorrelation, you will find out that even the equilibrium formula, again, using the same effective trap stiffness and effective time scale, yields also the same results with equilibrium conditions. And as a matter of fact, doing the same characterizations, MSU-Iligan correlation, and fitting with chi yields the same tau effective. So we are in a bit of a dilemma because now it turns out that the non-equilibrium steady state distribution is not sufficient to characterize the system. Okay, unlike in the equilibrium case that you do not need any other thing, for non-equilibrium steady state, you need, because these two analyses does not yield the same result. Okay, so again, that proposal for us is actually to calculate the transition probabilities, as I mentioned earlier, and to check how far that system is from equilibrium. By knowing how far the system is from equilibrium, then you can have another parameter to actually characterize the system at hand. So a very important parameter, or rather variable in this, is the transition probabilities. And so in this experiment, we were able to calculate the transition probability. So when you calculate the transition probabilities, it's basically amounting to properly accounting the position of the particle. So properly binning it. So for example, you bin it with some dimension, some distance, delta x, and then counting properly the number of times it goes to a particular region after some time delta t. Okay, and we were you can easily perform this and look that to your data. And here I would like to show you the transition probabilities if you scan the positions from XA to XB. We do long time measurements in our experiments, and so we are able to recover a lot of data to allow us to reconstruct this transition probability map. And what is interesting here is that you can see that, sorry, I forgot, you cannot see here the chi, right? Anyway, this is for increasing chi, okay? So this is chi equal to 1. The left column is chi equal to 1, and the right column is chi equal to infinity, basically, equilibrium condition, okay? So as you can see, at equilibrium conditions, the particles is highly confined near the trap center, okay? And the probability, transition probability map shows that most of the case is actually pointing towards this center here. Now, this is quite unlike, for example, for this case, for the higher, lower chi, wherein you see this large scale, how do you call this, fluxes, okay, in the transition probability. Now, our goal is to calculate the little balance-like relation. Sorry. I messed up with this slide, sorry. So we need to calculate two things, right? As I mentioned previously, you need to calculate the ratio of the transition probability from a particular position XA to XB, and also take the inverse transition from XB to XA, okay? And we would like to compare that transition probability over here to the case of the steady state. Okay. So as I have mentioned earlier, you have two sides in this detail balance relation. And if this two is equal to 0, then you are in equilibrium condition, right? So let's try to see this for different chi. For example, this is chi equal to 1 to 2.7, and then for the equilibrium case, which we call control. The solid curve here corresponds to the steady state, okay? The one we discussed earlier. This is the steady state, while the symbols, the black and red symbols corresponds to simulation and experimental data, respectively, okay? And you can see very beautifully that the steady state is really independent of the measurement of delta t, of course. But the transition probability is. So if you look at the red and the blue here, the black and the blue symbols over here, the range of the potential actually increases as you increase the delta t here. Okay, so it is really time dependent. Okay, and also another thing that we see is that at long time, delta t, at higher delta t, most of the potentials, both of them, are actually recovered. Although we still see deviations at long distances. Okay, so what can we expect, for example, in the equilibrium? Do we truly expect this? This is for the equilibrium case, it is trivial. Okay, although the time dependence of the transition probability from a particular position to x prime for the control experiments is very complicated. Okay, you can calculate this by hand. Equilibrium case, you can calculate by hand, and you will find out it's very complicated functions of delta t, for example. However, if you take the ratio of this with the inverse transition probability, this time dependence actually cancels out, and you are left only with this formula here. So you have exponent of k halves xa squared minus xb squared over kt, which is just or well-defined the Gibbs free energy in the case of equilibrium. Okay, and that's why for equilibrium case, as we can see over here, unlike the case for other values of chi, k star is equal to 0 at all delta t. Okay, so one can check this easily from calculations and also in our experiments and simulations. So this is verified for equilibrium. However, that is not the case in the other systems. As a matter of fact, you can summarize all these results by calculating the mean k star, which is just the ratio, or rather the difference of these black symbols with regards to these solid curves. Okay, the transition probability versus a steady state. And you can see from here, we look at for different delta t and also for different chi, that as you increase chi, indeed this k star decreases fast. Okay, as a matter of fact, around 5 is very near to 0 already. Okay, and this is again also shown in our simulation results, wherein such behavior is also expected. Okay. Now, what does this measure means? This measure actually has meaning, physical meaning in the concept of stochastic thermodynamics. The first term of this measure is actually equivalent to the entropy production of the system. Well, the second term is just the entropy production of the reservoir. Of course, when the system is at equilibrium, the entropy production of the system of the reservoir must be the same, right? And therefore, that is why we expect it to be 0 at equilibrium conditions. So the physical implications, therefore, of K star is that K star allows us to measure the distance of the system from equilibrium, and it is just the difference of the entropy production of the system with regards to the entropy production of the reservoir. Now, some in my group are, I have a collaborator who is now doing a lot of theory on this. I cannot explain a lot of theory. I'm no theorist. Wei Yin is. And so more about the experiments is that about this. Okay, so we now see very beautifully and show that as you increase chi, you have a controlled experiment to show that it can yield to equilibrium. This is for that system wherein the temperature is well defined. So the temperature that we work on here is well defined, and we just look at, by making the potential noisy. However, we would like to go beyond this and look at for the case where temperature is not well defined. Like for example, for the case wherein the fluctuations may not be necessarily Gaussian. Okay, so that leads me now to our second system of interest, which I will discuss, is about fluctuations of a Brownian-Rachet gear. But I don't know if I still have time for this, Wayne.
How many slides do we have, or
just few? I think I can make this quick.
okay.
Okay, so let me now go straight to this one. So I think everyone has already encountered Feynman's very famous Paul and Rachet experiment in his Feynman lectures. And actually, it was Mochowski who started a lot of these discussions before Feynman did. So the idea is that you have this Rachet over here, and they are separated by this box. And one side has temperature T1 and T2. So the question of Feynman is that the air molecules hitting this vein in one side, will it allow the Rachet to perform that work? Of course, the answer for this is no in equilibrium, right? Because it can just fluctuate. However, this will work if there is a temperature difference, specifically when the temperature in one side is not equal to the other side. And this is practically what you call Rachet motors, okay? Brownian-Rachet motors. And only quite recently have these Rachet motors been experimentally shown. For the case of, for example, here, Sokolov et al. Back in 2010, they have this very small gears, 48 micrometer gear in a sea of bacteria. Okay, and what they observe is that this gear, by the way, is not attached to anything. This gear induces net rotation. Okay, so you can see from here, and there is net rotation. Maggi, it all also did the same thing for the case of Janus particles. So this is biological, and this is now synthetic. And they do the same experiment, but this time in a sea of these catalytic Janus particles powered by hydrogen peroxide solution. Okay. Now, in all cases, what you can see is that this gear rotates. Okay. Now, our interest in this work is the fluctuations. As you can see in these measurements, for example, on Sokolov, you see a lot of these fluctuations. And these fluctuations are interesting because this is an active matter. So it's not necessarily Gaussian fluctuations. So we would like to check whether such fluctuations can be properly characterized, for example, by the measure that we introduced, K star. So if you're interested, we have this last year. It is very difficult to do experiments on that scale in the micrometer because it's not easy to control. And so what we did in the lab is actually to make a much bigger scale compared to that. So we make our own quote unquote living bacteria using these granular chains. And these granular chains under vibration can move by themselves. Okay, I hope you can see the video properly. And because they are heating this gear, they can actually make this gear rotate. Okay, so here is the time series of the angular rotation of the gear as a function of time for different concentrations. Okay, so 0.9 means this, there are many of them. 0.04, very few particles in the chamber. Okay, so as you can see, there is a net drift. Okay, so you see a net drift but also fluctuations. You can see fluctuations. Same as the paper, same as observations in bacterial experiments, we also see these fluctuations from this net drift. Okay, so the beautiful part, by the way, of Ratchet is that you can investigate, even though the systems are very far from equilibrium and quite complex, you can actually get some like thermodynamic results. For example, we have another paper wherein we show that this follows like a lambda-like transition. So we are investigating more about these transitions in the hope of, hopefully making some thermodynamic theory for this. If you're interested, we have also that last year. Now I go back to this result for the single gear, and as you can see, we were able to make a Langevin model for it, and from that model, one can calculate again the mean square displacement. Okay, so the mean square displacement has two terms. You have this drifting term and this ballistic term. Okay, omega squared delta t squared, where omega is the net drift, and dr is the rotational diffusion coefficient. And so here we plot the mean square displacement as a function of delta t, and we see very nice fitting of this form, especially at long time scale. However, at short time scale, we notice that this fits only very well for those cases wherein you have a lot of those particles, moving particles. We called it SPR, self-propelling rods. For systems that does not have many of them, definitely we see non-compliance to this equation for at short time scales. Now, as I mentioned, from the formula, we can extract also from the fitting two things. You have the angular velocity omega and also the diffusion coefficient dr, and we can plot that over here. So you can see there is this very beautiful peak, and for the dr, it's quite flat. Okay. For the angular velocity omega, this is very interesting that you have this type of shape. Our understanding, of course, is linear, right? So if you have more particles that will push it, you expect it to linearly increase. But that is not the case here. You see a rather decrease at some concentration of those particles. And I will show you that this is precisely because of jamming. Okay, as you have more of them, what happens is that as you increase the number of particles, okay, the time for the particle to stay at some region drastically increase, and also the drop, because now you have many of them. And so what happens is that this tau increases as a function of time. Okay, but nonetheless, even though you have those conditions caused by jamming, at higher concentrations of phi, you can actually reconstruct a simple formula to get omega. And basically, we did that, and we just modeled the momentum transfer of the particles to this region. We called it the trapping region of the gear. And if you properly account how many of that as a given time, this equation fits very well the experimental data. Okay. But again, our goal here is not so much of this the nature of omega, but rather the causes of these fluctuations in the net drift. Now, I take, for example, for the case of 0.54. Okay, so this is about 0.54 when phi is equal to 0.54. So if you plot phi equal to 0.54 as a function of time, that is the angular position. Okay, and so we are again interested on this part of the term, the fluctuation, because as I had mentioned earlier, this is caused by lack of particles, but this is caused by jamming. So these are two different regimes. We would like to see if the formulations that we have can characterize those regimes. And so what you can do is you can actually remove the net drift and look at the fluctuations based on the net drift. And so this one here, this theta is actually this angular position minus the net drift. Okay, and you can see these fluctuations. And here, just for comparison, I look at three concentrations. So you have 0.08, 0.54, and 0.90. and we look at the steady state distribution for those cases. Okay, and as you can see, sorry, I have to tell you that these curves over here are actually Gaussian fitting. Okay, assuming that is an equilibrium. Okay, it's easy to see from the fitting itself that this Gaussian, especially this end set over here, that this Gaussian fitting only works at some region very close to the to zero. Okay, going away from it, you already deviates from this non-Gaussian tails. And so again, this is a very clear picture of the system being far from equilibrium. But the nature of these fluctuations from a Gaussian perspective is different, the source. Okay, so we go back again to our formula we have been discussing for some time now, this K star, wherein we just look at and compare, for example, the result for the steady state with the transition probability. And this is the result. If you calculate both of that, I will not anymore show you the transition probability map, but nonetheless, this is the result for this one. Now, what I would like to show you, as I mentioned earlier, this is still we're still finishing this work, and would like to submit it soon. What we able to see is that even though statistically, as of now, given the number of data that we have, we already see that there is a net difference in K star with regards to having the fluctuations caused by jamming and having the fluctuations caused by just having a small number of them. Okay, and our goal here is to improve the precision of our measurements to actually look in much deeper and hopefully have a better picture on regards to this. Actually, my student have given me some results already, and but quite busy this week, and I was not able to update this. Nonetheless, we have a strong data now to support that K star somehow gives us an idea of that these two source of noise are different. Okay, so allow me to conclude. We have shown in the experiments, especially in the optical trap, that the steady state distribution on its own is not enough to fully characterize a non-equilibrium steady state. Okay, so the PSS has to be partnered with K star. Only that, then you can have a full characterization of an S, and that based on our initial results, actually with ratchet gears, we were able to show that K star can actually be used to distinguish the source of noise in active ratchet gauges. Okay, so let me end by thanking all my students. Most have been done by Jade. Mike is doing holographic optical tweezers. The ladies here have been doing simulations and granular, and the finding agencies that provided support for this experiment. Yeah, thank you everyone.
Thank you, Mark. So, any question, comment? No.
Hi, sorry, I may have a question.
Okay.
If I understand correctly, you said you can characterize the difference between equilibrium and non-equilibrium by the K star, which is the entropy production.
That's
right.
But
I am curious, how can you get the entropy production experimentally? Because in theoretically, you can take into account the particle number and maybe trace them if you are doing simulation, but I'm not sure how can you get this quantity experimentally. Maybe I missed the point.
Okay, so as we have mentioned, K star actually does not measure that entropy production, the total entropy production. Okay, the meaning of K star lies on the entropy production of the system minus the entropy production of the reservoir. So, but you are correct on regards to the measurement of the entropy production. There are currently tons of papers on regards to that right now. I can share some of this. One of them are quite good on this is Takehiro Sagawa. He actually visited Taiwan way in a couple of years ago, and yeah, he has extensively. There are now many ways to calculate that from time series data. Yeah, and unfortunately, I don't have time to discuss these techniques. But yeah, you can. There are now ways to calculate the entropy production on time series data. Yeah. But on regards to our work, we are not actually looking at the total entropy production because the total entropy production is just the sum of this. So we are more about the the difference of the of these two. Yeah. The interesting thing about entropy production is you can calculate them experimentally from what they call fluctuation theorems. So you can look at, for example, for the gear experiments, if you notice the gear can go this way and it can go this way, right? And so you have a delta theta for that. So the probability distribution of the delta theta will have results for negative and positive values. And if you take the ratio of the probability distribution of this delta theta and take the logarithm of that, it actually gives you the entropy production. So experimentally, that's how people are measuring it now. I heard some people are even doing that in quantum systems. That approach using fluctuation theorems, to calculate entropy production. Yeah.
So basically, you need to trace the probability distribution. Is that correct? You need to trace the probability distribution change. I mean, you have to infer the distribution in some way. Then you can.
Yeah. That is actually a important question. That is the beauty of non-equilibrium steady states, because if you look at the steady state distribution, it's not a function of time. So experimentally, you just look at all possible values, right? But if you look at want to measure the entropy production, of course, time is a particular thing. So you have to infer precisely. And the difficulty actually lies on the time scales that you are going to use. One has to make sure that those time scales are much smaller than the typical physical time scale of the system at hand. Yeah.
Okay. Thank you.
Yeah.
So because of the time, so let's thank Mark again. And Mark, thanks you.
Oh, thank you. Thank you for inviting. Hopefully.
Yeah.
Soon
okay.
I can be there.
Yeah. Okay. So then see you guys.
Okay.
Okay. Bye.
Okay. Thank you. See you.
Thank you, everyone.
Thank you.
Okay.